It's already final week. So this semester had really long the winter, and a couple of times the class canceled. But anyway, I believe we can successfully finish the scheduled chapter 1 through 13. If you check the textbook, we covered more than 600 pages. So, but we had one more important thing, that is a final exam. So after, I don't think it takes a time to finish the last of the chapter 13, then we will quickly review the second part of the semester, and you are ready for the final exam. Okay, so we are talking about basically the IO movement. So we had the last class we have talked about the IO structure. So basically the PC structure. So it has the PCI burst, is a burst, and through to the burst there is a controller for each IO devices. In case the IO method is simple, you can have the expansion burst that includes something parallel port, serial port, keyboard. Each does not require a huge size of the message. However, if we are using the I/O device that requires huge size of messages, such as such a hard disk drive, so it may be more complicated. Okay, so at that time we need specialized controller. Sometimes so we can have the special controller. Then finally we can transfer the data input and output. Okay. So we have seen the if we are using the register, here the status register and control register, the operating system need to check whether there is data that are available or not. So you need to keep checking that cause the busy waiting. So it's a busy recording the mechanism. So to address that problem, so we can use the interrupt. So we have seen that actually the current computer system and operating system is based on the interrupt signal. So that's a brilliant idea to speed up the computer system. Also to support the multi-user system and the multitask system. So because we have a very limited resource about using such an interrupt signal, and they can interrupt actually basically is a signal between hardware and the hardware, or hardware and software include the operating system. So we can use such an interrupt for the I/O, also for example, in case this control is ready, so you can send the interrupt signal. Then CPU initiate for example, it starts from the CPU, the processor. Processor need to access the data from hard disk drive. It can initiate the interrupt, and then this controller, I/O controller, it doesn't have to be only for the hard disk drive or the controller, disk controller, any the I/O controller, initiate the I/O by requesting the CPU processor. Then it will be the request message sent, and it will process the symbolic address to the physical address and read the data and return to the CPU. Then that is the basic idea of the interrupt-driven I/O cycle. And also, sometimes if we go through the CPU, so it will take a time because it's only the 1 to the 4 byte of the first in first out buffer. So however, sometimes if we think about your video file, so 1 gigabyte is how many IOs? So many IOs. So to bypass such the overhead, we can consider the direct memory access. Direct memory access requires the controller also, because anytime, anywhere, if you want to send a message in the computer system, you need this controller. This controller is a device, it's an electronic device that includes something very basic, register, instruction. Okay? So instruction and the register, then it can understand something interrupt or the message or some address, then the control your specific hardware. Then get back to such a data to the computer system. So PMA is the same thing. So if we want to bypass such a CPU to the data to the transmit memory. There are different types of the I/O interface from the application point of view. So we have seen such a yes. So data transfer, it can be character by character, such as the console or the terminal, and mostly when you read and input and output the data, that is based on the block. Read and write the data, that is based on the block. And also sometimes it's a sequential, sometimes random access. And we have seen the transfer, the schedule, it can be synchronous. Synchronous means you need to check when you send the data from one device to your operating either CPU. The CPU need to check whether the data is received and keep sending. On the other hand, asynchronous, it doesn't matter. You don't have to check it again. Instead, keep the whether or not the receive, you can keep sending the data. Okay, that is asynchronous. So we will see the example of that later. Also, we can have the network device, network I/O, which is based on the circuit program. The circuit program, you probably we did in the warming up, right? Warming up project. Most of the students utilize, except you, right? So most of the students implement such a circuit program for the basic communication. That was the reason that I assigned that. I think the couple of students, including me, use the other mechanism, data structure for such a process communication. Between the nodes, it's the same thing. The socket can be used for over the network. So using such a socket program, you can send what is this? This is from the database. You can send and receive input and output, the data, which is for the network device. So this is a blocking and non-blocking, synchronous and non-synchronous. For example, in case of synchronous, the kernel, your operating system, request the data and return the data, and during that time, your processor is ready. On the other hand, asynchronous is just requesting, then you don't know when you got the data. This one is faster and higher performance, but you cannot guarantee. You need to check the order of the data that you request. Yes. This is synchronous. Synchronous means you send the data during the time processor need to wait until you return the data. On the other hand, asynchronous, it doesn't matter. Just a request and doing the other job and keep requesting. So sometimes the previous one may return the later. Okay, so you are.
That's like TCP and UDP.
Oh yes, the TCP is the connection oriented, and the UDP is not. So UDP. So sometimes if you have the worse network status, the UDP is just to keep sending. So from the receiver side, you need to check verify the data. I think that we have done kernel I/O system. So we are going to see some I/O system that can support some kernel system that can support the I/O. So the first is the scheduling. So we have seen such a I/O scheduling in the file system management. In the file system management, each device has for example, here, each device has their own request. For example, this one is a laser printer. Laser printer will use the spool. I think there might be, yes, like the spooling. The spooling is another type of the I/O device, I/O, the data structure. The spool, for example, the spool is used for the only printing job in computer system. So for example, when you send the printing job, can you divide the printing job page by page or the half page, and you can pair the first half page for your request, next half page for your. You cannot do that. Once the printing job is started, it should be done. So entire job should be completed. So however, you can. So if we have the share over the printer, you can send the job. So there might be scheduler. So this scheduler can consider just a first in, first out entire job. It will not be the stop in the middle. So that is a spool. So for example, that can be managed in the schedule for each device. So similarly, hard disk drive may have such a I/O scheduler, and some other for each device may have. So that is the one of the I/O subsystem. Okay.
But this now, the caching and spooling isn't it a part of a memory on the printing or scanning device?
So this one we will discuss later, okay? But it's in terms of I/O, we can make such a caching for it can be the main storage, like the memory, okay? Nowadays, each device has even the cache area. So I'm going to explain after we finish this part, okay? The next, the system as a part of the kernel I/O system is the buffer. What is the buffering? Where can you find the buffer? Like the highway. So you can see the buffer area.
Yeah.
When you exit the lamp, right? Why? Because the speed of the car is so fast. If you hit the wall or guy, it will be damaged, right? So buffer can absorb such energy. Similarly, when we have the different speed of the network or the device, especially in the I/O system, so some media is very fast and the other media is very slow. But sometimes you need to communicate, send a message and receive the message between two media which are huge gap, the speed. How can you address that problem? At that time, you can put a buffer. When you watch the video, okay, the real-time video streaming, sometimes it's a buffering. Why? Because the sender, the provider is sending the data very fast, or it's slow. But I can display very fast, 1 Mbps, but they send, my network is 100K, the Kbps speed is 10 times. So then after watching the 1 second and wait the 10 seconds, watch the 1 second, 10 seconds. It's really bothering me. Instead, why don't you wait 1 minute or 10 minutes? Then make the buffer. We keep such a data, information, then read the data from buffer. So that's the same, exactly same idea. This is one very popular interview question. What is the difference between the cache and buffer? What is the main difference? Cache and buffer. It looks like very easy, but during the interview, it's not easy to answer quickly.
Cache is just stored the old previous data, but buffering is the live data.
Both of them actually store the data.
Yeah.
But buffer is to bridge the gap of the speed. Okay? Faster media and slow media. Fast car and
Slow.
not slow car, it's the nothing move. Okay? So it's to bridge the gap in between. So faster speed and slower speed. Cache is the reuse. Okay? Reuse the data. So that is a cache. So we will see the cache. Cache also used further to improve the performance of I/O system. So buffering. So sometimes you can have double buffering. Double buffering means I have the two buffer. So one buffer is receive the data from the slow media. Then once it is cleared and serve for the other faster media. At that time, other one can be used for the buffer keep receiving. Because if we can use the one buffer for receive and serve for the data, but there can be a bottleneck. So once one is filled answer for the master media, the other buffer can be used for another buffer. So that is the double buffering. So we have the two copies of the data. Usually one of the issues in the buffering is what is the optimal size. The bigger is the better? No. The bigger means you need to wait more time. Longer time you need to wait to receive the data. So optimal size. So that is the reason when you are using the window media player or the something in the display media, so you need to set up the buffer size. That depends on the user, the satisfaction or the quality of service. Okay. So each device has their own status table that can be used for the scheduling.
So why do we need double buffer?
Double buffer because if we have the one buffer, it can be used at the same time, receive the data and send out the data. So it can be the bottleneck. Okay, buffer is anyway the data structure, so it can be the bottleneck. So why don't we switch buffer? So once this one is full, then it's to use for only serve, send out the data, and the other buffer will receive the data. So it's a double buffering. Okay, for better.
So what in that case, both will not have the same data, right?
That is the better. Okay, so you'd better have the different disk control or different media. And another subsystem for the better performance of the I/O is caching. As I said, the caching is usually in the main storage, which means the memory. Okay. However, nowadays even the device itself has a caching. Okay? So it has a memory, so it can be served for the cache. So that is the cache and spooling I already implemented is that is only used for the printing. So in case we cannot divide the job into several pieces, so we can use the spool, then the user can send the job to the spool. Now for 250. For excessive job, so we can reserve the specific device. Yes. I/O protection, just like the memory protection, the memory protection is more important because memory is nothing but the address, the set of the addresses. So if you know the address, so you can easily change the data. That can cause a lot of problem. Actually, it's a real problem. Similarly, the I/O also may cause such a problem. So we need to protect such I/O. So how can we do that? So we can specify the privilege. Okay, so ownership of that, the I/O. Okay. I'm going to skip the power management. And the example. Okay, so that's pretty much it for the I/O system. So I'd like to wrap up the semester, and we'll finish the last lecture. So during the semester, we have discussed about the three main parts, the operating system. I still regret I was not able to offer the exercise lab. So if I need to offer the couple of more years for operating system, I will definitely offer the exercise lab where the student can rebuild the kernel and you can can add the algorithm or your project. You have done the 2 projects, right? Couple of projects, scheduling and page replacement algorithm. Such an algorithm can be part of your kernel. So you can rebuild the kernel. What about the kernel itself? The kernel itself, you can compile as a program. Okay, it's a group of software. But unfortunately, I didn't have a time even. So as you know, the major part is the data and data management and so on. So I spend a lot of time to prepare the new process. So I didn't have a time. But so if I have a time, so definitely I will offer the exercise lab where you can modify and test and rebuild such a kernel. But if you are interested, I think you have enough programming skill, so it's not a big deal to recompile, rebuild. Even textbook has the exercise lab to rebuild the kernel, the Linux kernel. So Linux is open source, so you cannot rebuild the Microsoft Windows kernel, but you can do the kernel rebuild with the open source. So why don't you try such a thing? Then, in the first part of the semester, we have talked about the process management. Process is actually everything of the operating system. Then we have discussed our data structure of the process and the thread and the synchronization problem and so on. Then you have the midterm exam. And after the midterm exam, we have one more chapter, which is so deadlock management. So deadlock. So first you should know what is the deadlock. So there are the 4 requirements of the deadlock. Okay, what are they? Anyone remember?
When resources are not available to the project at that time, deadlock will occur. When resources are not available for the process, at that time, deadlock will occur.
This is the characterization of the deadlock, right? So mutual exclusion, hold on, wait. Mutual exclusion. Can the one process cause the deadlock? No, it should be the 2 processes, right? The 2 processes, if they are doing their own job separately, there might be no problem. If they hold and wait, okay, they may cause a problem. It's greedy because of the greedy characteristic of the process. It may cause the deadlock. Then no preemption is no backup. I don't want to give up and I don't want to restart. So I'd like to keep going my way. Then the most important part is circular way. So circular way is actually the hold and wait is part of the circular way. Anyway, this is a full characteristic of the deadlock system. You should understand that. We need to address that problem. It's a simple chapter. So how can we address the deadlock problem? Deadlock prevention. Deadlock avoidance. Deadlock ignore. Deadlock prevention, deadlock avoidance, deadlock detect. Even I forgot. So deadlock prevention means by allowing at least one characteristic. Okay? No preemption, but you allow the preemptive process, which means you can restart. Then there might be no deadlock. Circular way, you never have the circular way. Okay? Only serial lies over the resource, getting the resource. Then there's no deadlock. So deadlock prevention is you can allow at least one of the requirement characteristic. Then it's a prevent, you prevent deadlock. Deadlock avoid. So in case there is a request of the process, you can check whether this request caused the deadlock or not. How? Using resource allocation graph. So you should be able to understand the resource allocation graph. Okay? So at that time we have learned Banker's algorithm. I still don't know why it's a Banker's algorithm. So, but anyway, it's called the Banker's algorithm. So we can have, this is a deadlock prevention, deadlock avoidance. We can find the safe state. If safe state, so that is, okay, so for example, here. So using the resource allocation graph by applying the Banker's algorithm. So this is the safety algorithm to find the safe state. However, I ask you, do not try to understand this deadlock avoidance algorithm using this slide. Instead, why don't you try to understand the example? Okay, that is, I believe that is the best way. Everybody can understand. It's not very complicated. So this is an example of the Banker's algorithm. Definitely, exam will not be the same number as this one. Okay, so you should be able to find whether this is a safe state or not. Safe state means if you can find such a sequence of processes that can be completed, then it's a safe state. So there might be no problem. So you can allow to such a request. That is a deadlock avoidance. It's a before you enter. Okay, before you allow the request. So I need one more hard disk. I need something. Before you allow such a thing, so you can apply that algorithm. Then deadlock detection means you can allow any request, but periodic time you can check whether there exists circular wait one using the same algorithm. So almost the same algorithm, but the deadlock avoidance is before you enter. What if I allow this request for the process, whether deadlock or not, safe state or not. But deadlock prevention difference is different. Deadlock detection is you allow any the request, but from periodic time you need to check using the almost the same algorithm. That is the deadlock detection. What if you detect the deadlock? In other words, what if you detect the circular wait? You need to find the victim. Okay, so you need to find the victim process. So that is the deadlock detection algorithm. That's pretty much the chapter 7.
Professor, one question.
Yes.
To determine that there is a deadlock, we need to find like the 4 different situations.
Yes, 4 different situations. If the current situation satisfied with the 4 conditions, that is a deadlock.
So like the 4 of them have to be present, like not 3 or not 2, the 4 of them.
Yes. So if at least one of them is not satisfied, that's not deadlock. So you can solve the problem. That's a deadlock. Actually, the idea of the deadlock prevention. Okay, then the memory management. So main memory management, and I think the main part of the memory management is you need to understand what is the logical memory, what is the physical memory. Then for the physical memory, eventually we will not in chapter 8, but the next chapter we will use the page. So it's in the project you implement the page replacement algorithm because the physical memory page frame are not enough. Okay, so in the memory management, so to protect the memory is used for the processor, right? So it has the instruction, it has the data, it has hit area, it has the stack area temporary. So that should be protected. How can we protect it? Using the address as a base and limit, because we don't know where the process is located. So, but we know the size of the processor, so we know the starting point of the processor. So using such a base and the limit, we can protect the process, the memory. Then, what about your compiled program? Compiled program, you don't know exact address, physical address, until it is loaded into the memory. Depending on the situation, sometimes it's lower address, it can be higher address. So to address that issue, process has the relative address only. Even your higher level programming, it has just a symbolic address, like the integer I. But when you compile it, it has the relative address. In other words, offset. Okay, offset means how much far from the beginning of the process. So then we need to bind such an address during the link and this one was the link during the link. First one was link and load. Okay, link and load, it will be binding. So this one shows the different address. So actually the same, but this is a symbolic address, and then the relative address that is offset eventually is a physical address. So memory management unit is the table. This kind of table we will use throughout the memory management. So you should be able to, it's a mapping table. Okay? So mostly the left-hand side is the logical address, right-hand side is the physical address. Using such information, you can find the logical address to the physical address. Definitely, there will be the question. So we did a couple of the examples in the classroom also. So if without understanding such a mapping mechanism in the memory address, if we have the unlimited resource on the memory, we don't have to worry about this because it has the relatively small the resource on the memory, so we need to the map. Okay, sometimes it's in and out, page in and out, because we have the less space on the memory. So MMU is one of them. Where does the MMU located? Stored. It's also memory. So which means CPU should have the register that has the starting and size of your memory, the management unit. This is the memory area. Nowadays, swapping. Swap means originally swap process by process. Entire process swap out from memory to the hard disk drive, and hard disk drive to the memory is swap in. So swap in and out. However, there is the traditional concept. Nowadays, the swap can be used for what? Swap space is used for virtual memory. We will see the virtual memory. Virtual memory is the extension of your physical memory. So this is the swapping. Mobile device is slightly different. So only one process is active, and there is no background. Okay, because it's limited the resources, specifically the power management issue. So in all the operating system, the memory management, we can allocate the entire process, big chunk of. So for that allocation, we have the several simple idea: best fit, the worst fit, first fit. Something like that. I think you guys can understand easily this one. What if we combine some the logically the similar or same the part of the program? So like we can make the group of the chunk. Okay, that is the segmentation. Yes.
For the worst fit, we have to take the biggest size first, right? Worst fit.
Worst fit will generate the small or the biggest. Yes.
First, yeah.
Best fit means the smallest leftover. So that is the best fit. But we cannot say which one is the better than the other. It depends on. Okay. So like for example, even worst fit can make the bigger size of chunk. Best fit make the smallest never be may not be used later because it's small.
And if we use one block, then we can't use the same block for the second process, right? I mean, if my process needs 100K and I have one block of 200K, so I will use that.
So at that time, you can use the first fit. So in case you have the same size of the flip block.
No, I want 100K and
Yeah,
my block is for
100.
200K, right? So, and for the first fit, I will use this block.
Hmm?
So the 100K will be my external fragmentation.
Yes.
And I cannot use it, right?
If you have the 50K, the memory, the process, it can be used.
Okay.
Later.
So I
So
can put two
the
processes.
memory is like 500K, and you have two processors of 100 and 200, so it can go in the same memory.
Yeah, because it's a full chunk, okay? So this one is the oldest approach. So which means we are not going to segment, we are not going to make the page, we can upload, we are going to upload entire process. Like for example, if we have the 500K, the process, we have first time the 1/8, I think that we have the example of this one. For example here, this is a whole, and this is a whole, this is a whole, this is a whole, it's a free. So 600 free, 600 free, 400 free. So even though we have the total 1,200, 1,600, so in case the 1,000K, 1,000 the process, we cannot load it to the memory because it's segmented. Okay? That is the allocation. So you can realize it has a lot of the external fragmentation issue. So to address that problem, we can use page mechanism. So paging can reduce huge the external fragmentation, but still has internal fragmentation. What is the internal fragmentation? Some of the students got confused. Like for example, if you have if you are using the page size, the 512 byte, you have the 500 byte process. The 12 byte is limited. You cannot use 12 byte because it's inside the page. That is the internal fragmentation. So this is a page. The page frame means it's a physical memory. Page means so logical memory. What does it mean, logical memory? That's another thing that the student confused. The process, program, your program is the logical memory. Okay? Our job, operating system, in terms of the process, the memory management, main job of the memory management is what? How to allocate the program into the memory. Okay, so we can use the traditional way, the allocation, entire process, that causes a lot of the fragmentation. So using page, so our job is to allocate the logical memory, that is a process. Okay, then this process, the page in this process allocate to the page frame. It doesn't have to be same order. Okay, we will see the example like this one. Like this is a logical memory. Means what? It's a process, your program. When you start your program, okay, this is a process. It will be loaded into the memory. At that time, not all chunk of the process will be loaded into the memory. Instead, we are going to segment by page. So this is a logical memory. Page 0, 1, 2, 3. So how many pages do we need? 4 of them in the physical memory, which is called page frame. So I found this one for page 0, this one page 1, this one page 2, this one page 3. We need to have the mapping table, that is a paging table, similarly MMU. Okay, that should be loaded in the memory also. So when CPU need to access the instruction in the specific page, first take a look at the register of this page table, P, P, T, R, S, T, R, right? You don't have to worry about the name of that register. And using this, the mapping logically is here, so 1 go to the physical memory address. That is the paging. Any question regarding to the paging? So because of the name, many of the students are confused. Logical memory means what? Process. Okay? is your process. And physical memory is the page frame. So you can just mapping, simple mapping. So there is another example of that. So this is a real example. So in this case, we are using 4-byte sized page. So just 4 bytes. In real case, mostly 512 bytes. But here, we are using to simplify the problem, 4-byte page size. And physical memory is your physical memory in your computer. Definitely, it's not much bigger than 32 bytes, but we are pretending the sample of the computer. So this is your physical memory, 32 bytes. This is your program, okay? Let's say it's a word program, okay? It has a 1, 2, 3, 4. What does that mean? A, B, C, D, E, F, G. That's an instruction, okay? In your program, it's an instruction like the move, okay? Or I, integer I, or the increment, decrement. It's an instruction, but simplify the content of that page. Then there is a page table. Using page table, 0 logical memory page is mapped to the physical page frame number 5. 0, 1, 2, 3, 4, 5. So A, B, C, D, A, B, C, D, you can find the same pages. Okay? So mostly I'm going to ask the question like what is the address, physical address of the cake? For example, you already did in your pop-up quiz as well as the quiz. Okay. Any questions?
Yeah, can you calculate that address?
Yeah.
The best way is if you understand this slide, you don't have to calculate. Okay? Don't try to memorize the question. But how can we calculate? So for example, if I need to find the address of the G in physical. Sometimes, one time I asked the exactly same question, then asked the physical memory address of G. Actually, you can count over here from the figure. You don't have to calculate. That was my mistake. So in this case, so if you want to calculate, so that is after that I made the pop-up quiz, okay, without the figure, only using the page table. Do you remember the pop-up quiz? It doesn't have the picture because I gave the picture. Then the answer is here. Like for example, G is where's the G? So 24, 5, 6. So 26. But if you want to calculate, that is, you can, what is the size of the page? It's a 4, okay? Where G is located, it's a 0, 1. Logical page number, 0, 1. 0, 1 is mapped to the page frame 6. So it's a 6. So 6 times 4, 24. Plus what is the offset? 0, 1, 2. So plus 2, so 26. Okay? Got it? Any question?
Yeah, can you repeat because you were covered and I didn't see it.
This time, I'm going to.
Thank you.
So easiest way is G is here, G is here, 4, 5, 6, 26. That's it. But in case there's no figure, okay? So what is the page size? So 4. Okay. Then what is the page number? Logical page number of the G. So 0, 1. This is a page number. Then 1 is what happened? I really don't like this. Okay, I'm still there. So 1 is mapped to the 6. What is the 6? It's the frame number. 0, 1, 2, 3, 4, 5, 6. Okay? That means 4 times 6 is 24. Then you need to check the offset. 0, 1, 2. Offset is a plus 2. It's a 26. That is 26. Okay?
is one of the question, right? Index.
I don't know. I don't make the question. Okay, so page table based register, that's a PTBR that I mentioned, that I programmed. Then the others are the enhanced version of such a page. What if we have the many pages? That's true nowadays. The memory size is sometimes 8 gigabyte. I think even this one is 4 gigabyte or 8 gigabyte. So at that time, we can use the hierarchical paging or hash page using hash function. Inverted page is the opposite. Inverted page means, so usually when we make the index, it's a key then value, but you don't mean the opposite. So for each key, then number. For example, web pages, when you are using the Google or the Yahoo, Bing, so that is based on inverted page. Inverted page means for key is the index based on your key. So for example, if you type the University of Bridgeport, how many pages? Each pages are linked to that. Okay. So similarly, so when we build the hierarchical page, it's like the indexing, 2 level, 3 level, and the hierarchical level, and hash, we can apply the hash function. Okay. Inverted page means for each the process ID, then we can have the page number. Okay, that is the memory management. We have a virtual memory. Virtual memory is the extension of the physical memory. So nowadays, such a concept of the virtual memory used for swap. So when we are saying the swap space, that is the virtual memory. Okay, that is the definition of. So instead of the entire process swap in and out, so if we already adapt the idea of the pages, so we can page by page in and out. That is called the page in and page out. Okay. So what is a page for? So in case the CPU cannot find the specific page on your physical memory, that is a page fault. So page fault usually require what? Page in and out. So you need to bring if you do not have the flip pages, you need to page out, then bring the specific page into. That causes the overhead. So number of page fault is one of the indicators whether your system performance is good or bad. Okay. So the problem is in case we do not have the free pages, okay, no free frame, then that is a problem. We need to address that. How can it be? There are algorithms. That's your project B, second project, right? That is page replacement. So this slide shows the overall process of the page replacement. I believe that you guys now understand how it works because you did your the project. So, what is the algorithm? First in, first out. Okay, so using the reference string. Each number indicates what? Page number. Okay. So, first in, first out. We try to find the victim based on the when arrival time, when it is arrived to the physical memory. This is the case of the 3 frame, 4 frame. In general, the number of more the page frame will be the better, which means the less page fault, not always because of the delay anomaly. So which means for example, the more page frame you have, sometimes the more the page volume. So it depends on the pattern of the reference string. And we have first, this is the first thing. First off, optimal algorithm, take a look at the future. That will be optimal, so which means if we will be used the later, you do better keep, not use, just a victim. Problem is the ideal case. There's no way to see the future, right? So it can be used for comparison, like the reference. So why don't we take a look at back the history? That makes sense. You can keep the history. The recently used the LRU algorithm. The database course just before, the database used a lot for such a LRU algorithm. That's the. However, the LRU algorithm need to keep the history. So how much when was used? Because it's along the time. So we can use the one bit for the counter, not bit byte for the counter, or we can use the stack, the data structure to keep the history of them. Also, we have the extension of the LRU algorithm that is called the approximation, LRU approximation. Instead of the keep all the history, why don't we keep the certain period of time of the history? So that is the reason it's called the LRU approximation